Welcome. In this lecture, we have already completed the lectures on LD steel making, and in this lecture, we will discuss about the hybrid processes. So, hybrid, as the name suggests, it is a combination of two processes, LD plus something. Okay, we'll discuss. So, significance of the hybrid process first let us discuss, and then we will discuss the performance of the hybrid processes. So, need for the hybrid blowing, right? What is that hybrid blowing? Actually, if you see the LD furnace, actually here to start with, so lens is here, and you have the bath like this, some crater formation is here, and this somewhat like this. Okay, it is not exactly okay, fine. Right. So, some crater is there, and then this is the bath. So, some crater has formed, and then the liquid will move in this way, that is this way, and then this is this way. Okay. So, this is only the upper part, that is it is moving, since it is moving in this way. Okay. This is the way, that is the liquid is moving, because the jet is forming, that is, and then the liquid is basically in the surface will move in this direction, that is the way. So, there is a circulation loop it will form. When you give the jet, there is the crater formation, the liquid moves this way, and similarly you will have this very weak loop formation here, that is, you can see in the bottom part the loop will be little weak. So, another loop will form, that is the velocity loop, but this will be the weak loop, because the momentum is transferring from this upper loop to the bottom part, that is because the oxygen jet directly interacting with the upper part of the furnace. If you see the liquid, you can divide the liquid in two parts, upper part and the lower part, and jet interaction basically with the upper part liquid. So, upper part liquid is strongly stirred, that is why I have write like this, and the lower part liquid is weakly stirred, that is why I have given by the dotted line. That is the major problem in the LD furnace. So, in the LD process, the lower part of LD is not well mixed. So, what happens is that whatever the carbon impurity percentage here, this is the impurity which is residing in the lower part may be rich in impurity even after long time of blowing period, because here the impurity will be diminished very quickly and it will be mixed up, although, because thing is that the liquid from the upper part going into the emulsion, and then they are coming down, and then it is mixed up totally. So, upper part, because the mixing is very high, so its impurity concentration will go down significantly with time. But in the lower part, the impurity may even very rich even after some period of blowing period. Okay. So, and then that is the thing, that is the well not, if it is not well mixed, then that is the problem, it happens. Okay. So, therefore, the liquid in the lower part of the furnace may remain rich in carbon even after significant blowing time, when the carbon concentration in the upper start part of the furnace has decreased significantly. That I was just telling. When the impurity is low, here the impurity may be quite high, there is the carbon specially. So, it may be the carbon rich, and a certain movement of the liquid. So, and then what happens, suppose you have certain amount of liquid, and the liquid can go always. So, suppose a packet of liquid, when it is moved up, when this liquid, suppose a part of the liquid is moved up here, and then it joins the emulsion phase, here is the, and then it goes to the emulsion phase. So, you know this is the emulsion, this is the emulsion, here it is the emulsion, right. So, bubble droplet, and then this is the emulsion part. So, if certain liquid, there is some pocket of liquid rich in impurity, it comes to the upper part and then suddenly goes into this emulsion phase, then there can be a burst of decarbonization, because this liquid is very rich in carbon even after certain blowing period also, because this part is not mixed up. As a result, this is rich in impurity, rich in carbon, and when it goes to the upper part and subsequently go into the emulsion, then there can be certain burst in the decarbonization rate. And if it happens, then what will happen, what is that called, that is this foam, there is the height of the foam and the emulsion can increase, okay, and then it can also come down. It can also come down. This is called a sloping phenomena, okay. So this type of phenomena is called the sloping. Then sloping is sudden movement of the liquid from the lower part to the upper part, and subsequently in the emulsion gives a sudden burst in decarburization, and that is called a decarburization, and that gives rise to increase in the height of the your foam and the emulsion can come out of the mouth of the LD furnace, and that phenomenon is called the sloping. Just like our sloppy nose, that is the LD mouth is also sloppy. So it is sloping, that is called the sloping, okay. So the material will come down, you have a lot of iron loss that is there. So that can happen, okay. And improper mixing in the lower part also keeps the process away from the equilibrium, because since it is not mixing properly, so it will be away from the equilibrium. As a result, the partitioning of the impurity will not be very good, okay. There is it will affect the partitioning of the impurities, lower partitioning of the impurities. So the process will not be very efficient, okay. So two problems are there. One thing is that if you use only the oxygen, that is the LD process, since the lower part is not mixed properly, two problems can take place. One is that sloping problem, another is that the because of lack of mixing, you will be away from the equilibrium. So partitioning of the impurity will be not very efficient, right? So this problem is there. So that's why you do oxygen blowing, and also sometimes that is you have inert gas purging from the bottom, that is the gas purging is there. So from this is called the gas purging from bottom. So if you do gas purging from the bottom, then this will again be strong loop, a strong loop will form, and then the mixing will be very good, and then sloping will not be there, and the process will be more close to the equilibrium or with a better partitioning, okay. So that can happen. So if you can properly use, that is called the hybrid blowing, that is the oxygen lancing from the top and the inert gas purging from the bottom, then then you can have a very good mixing, and this process become close to the equilibrium, and sloping probably will not be there, and this is called a hybrid blowing. That is called the hybrid blowing. This is called hybrid blowing, that is the blowing from top and bottom, okay. And there are wide variety of hybrid process. Not only that, this is only one aspect, and other aspect is that if you want to treat a very composition of the hot metal is different, very high containing phosphorus, like more than 1% phosphorus, then sometimes you use the lime powder also, either from the top, from the bottom, lime powder, such that the basic slag form, early basic slag formation is feasible, okay. If you use the lime powder, then you can form because you can enhance the rate of CO dissolution, right. So those are also called hybrid process. So there are from blowing point of view, there are several hybrid processes are there. Besides from hot metal composition also, you have other hybrid process. So we'll just discuss the different hybrid processes now, okay. Okay, so now this is the hybrid process spectrum. There are a lot of hybrid processes. First of all, the classical LD with only top blowing and the lumpy charge from the top, that is called the LD, right? And then you have a LDSE or the OLP process, LDSE. So then LDSE or the oxygen lime powder is called, or LDSE process. Process with top oxygen and the lime powder from the top. Lime powder from the top, as I said, if you have a lime powder, then you can treat the high phosphorus hot metal, right? Because the lime dissolution become faster, you can form early basic slag, so you can start dephosphorylation from the beginning. That is the idea, such that the dephosphorylation ends before the carbon ends into the system, okay. So this is, and then LD with additional bottom gas purging, that is the thing I just talked about in the hybrid blowing. This is called the LD, ladle bubbling equilibrium. That is, if you do the ladle bubbling, that is from the bottom, if you just give some inert gas, then the bottom part also mixed up very properly, so you can move more close toward the equilibrium. You can increase the partition coefficient, and you can be very close to the equilibrium because the mixing is strong, because top mixing, upper part already mixed, and the bottom part also you can make a good mixing by bottom gas purging, inert gas purging, and if you do that, then you move towards the equilibrium. That's why it is called the ladle bubbling equilibrium, okay. Then LDAP, LDKG, there are the other process variant of the LD with the additional gas purging from the bottom. Oxygen blowing from the top and bottom. There are processes where you are charging partially the oxygen from the top, 70%, say 30% from the bottom, or you are charging 90% from the top, 10% from the bottom oxygen. So, instead of giving the inert gas from the bottom, you are directly charging the oxygen from the bottom partially. Okay. So, that is the oxygen blowing from the top and bottom, BSC, BAP, LD, OB process, etc. Oxygen blowing from the top and bottom, both oxygen blowing from the top and bottom, and with lime powder from the top. Lime powder from the top and oxygen, that is LDHC, STB process are there. Oxygen blowing from top, bottom, and lime powder from the bottom, just little process variant. Here you are charging the powder from the bottom. Then you can see oxygen and lime powder from the bottom only. Oxygen and lime powder from the bottom only. There is 100% oxygen from the bottom, and this process, this is the number 8. This is also very classical OBM process, oxygen bottom blowing method. And here the oxygen is completely charged from the bottom. 100% oxygen from the bottom is charged. That is called the OBM process. Okay, and a protective hydrocarbon, because it has a, through the annular portion of the nozzle, I will just talk about that thing. It is a basically hollow cylinder. I will talk about that thing. That is, you also use a protective hydrocarbon from the bottom, such that when the hydrocarbon cracks, it is an endothermic process. Because problem from the bottom injection is that if you inject the bottom from the bottom, oxygen from the bottom, then heat generation at the tip become very high, obviously, because oxygen react with the impurities and forming the heat, and the tip of the nozzle get eroded very fast. Okay, that is the thing. So, if you want to protect the nozzle, then sometimes you used some hydrocarbon through the annular portion of the your nozzle, such that when the hydrocarbon comes out, it reacts, it basically cracks and forming the carbon and hydrogen, and that carbon and this cracking of the hydrocarbon is a very endothermic process. So, that basically reduces some amount of heat around the tip of the nozzle. So, that basically compensates the very high heat at the nozzle because of oxidation process. Okay. So, that way you can maintain the nozzle, bottom nozzle. So, that is the major problem actually. Otherwise, oxygen blowing from the bottom has been found to be very good from the mixing point of view, and the process is very close to equilibrium and with the minimum iron loss and with the maximum partitioning achieved. But problem is the nozzle maintenance. In spite of using the protective hydrocarbon, the nozzle has to be replaced regularly. That is the problem of the OBM process. And then a little variant of the OBM process is the oxygen and lime powder from the bottom. You can use the lime powder also, and then oxygen bottom blown plus the oil and gas injection you can do. Then oxygen and inert gas from the top only, oxygen from top only but with the jet pulse, that is the oxygen with the jet pulse, then oxygen from top only with the circular motion of the lens. So, there are various process variants are there of this hybrid process. Now, various design of the tuyers, you can have a straight pipe also may be there, or you have a directed porosity through the channel bricks, you can have porous plug, you can have permeable membrane, that through which the gas will come, and then some other nozzle design you can see STB process. Here you can interestingly you can find the CO2 is also charged, CO2, argon and nitrogen. So, and the annular portion also you are charging, that is you can see this is the nozzle where basically in the annular portion you are giving carbon dioxide, argon and nitrogen, and through the central portion, there is the central part, you can give the oxidizing gas, mainly the oxygen. You can give the carbon dioxide also, CO2, argon, both are going through that region also. And basically when the carbon dioxide, very important reaction take place, carbon gasify basically this reaction CO2 plus C forming twice CO. So, this reaction take place here because the dissolved carbon react with the carbon dioxide forming the carbon monoxide gas, and this is a highly endothermic process that basically helps in protecting the tuyere. So, always the CO2 you can find, the CO2 through that annular portion is goes, and then there are other variant also. You can use the hydrocarbon also, that is the cracking. So, you can see hydrocarbon always through the annular portion such that it cracks here and the heat is generated at the nozzle tip, because of oxygen. Oxygen goes through here and then heat generated, and there is the cracking of the hydrocarbon in the annular region basically try to reduce the heat generation at the tip of the nozzle. So, it can maintain the nozzle to some extent. Okay. So, then all process variant, oxygen plus lime and the propane natural gas as the protective gas, and the oxygen and lime through the bottom, the KMS, KVUP. So, several process has come. Now, extent and the type of gas injection from the bottom, you can see the extent and type of the gas injection. You can find most of the cases there is the wick starting from the bottom, there is a percentage of gas, there is a percent of gas from the bottom less than 1%. So, these are the, so in the most of the cases you can find it is within 1 to 5%, 1 to 5% you can find 1 to 5%, even less than 1% also. LDKG process, it may run with less than 1% of gas. So, gas from the bottom is not very large amount, and this is the wick stirring you can say, and in this region is the moderate stirring, right. And most of the process like the LB process, it is in this region, weak to moderate, right, that is within 1 to 5%. So, 1 to 5% gas injection from the bottom, inert gas purging from the bottom is the regular thing, and you can have weak also, and you can have moderate. LDOB process can be moderate also, that is it may exceed 5%, and when it exceeds the 20%, it is considered the vigorous stirring. Okay, some processes are there like KBOP, KMS process with the vigorous stirring from the bottom, and in case of the oxygen bottom method, bottom blowing, that is 100% oxygen. So, it is basically the, it is 100%. So, that is the 100%, OBF is 100%, right. So, there is the extent and type of the gas injection. You can see what are the gas injection you can find, that is the LD, no bottom injection, then the LDKG, inert gas, all are the inert gas, LV process, inert gas and oxidizing gas. In case of the STB, oxidizing means you can have CO2 also in STB process. BSC, BAP process, air and nitrogen they charge. LDOB process, oxygen and hydrocarbon. If you give oxygen, you always give the protective hydrocarbon also, because here it is also in the moderate range. And in this case, right, KBOP, KMS and OBM process, all everywhere, hydrogen, oxygen and hydrocarbon is essential. When you exceed vigorous, if you give the oxygen more than 20%, then your hydrocarbon is essential actually to protect the nozzle. Okay, because the cracking of the hydrocarbon will endothermic reaction that helps in reducing the temperature of the nozzle tip. So, this is, and then another parameter is very important. So, this is the different process variant you can find, and mixing time, you can see the mixing time, and with the flow rate of the bottom gas, there is the gas flow rate from the bottom, this is the mixing time, and you can see the mixing time for different processes. What is called mixing time? Mixing time is, suppose it can be measured by tracer actually. You can laboratory, you can do that. Is if you have a reactor, suppose you have a reactor something here in the LD vessel or something here, and then you insert some probe here, and then you add some tracer and you see how much time it takes to attain the 90% of the average concentration. Suppose you add dm amount of tracer into this bath, right, and the bath volume is V. So, this is the concentration, average concentration. Okay. So, if you add certain amount of tracer in a bath, and bath is mixed up, okay, regular mixing is there. So, you have some stirring mechanism is there, your mixing is, this is the average concentration, dm you have added just at one time, and the volume B, so average concentration. And if you insert some probe, and through this probe you are measuring the concentration at this location, say, then what will happen, the concentration with time it will go up increasing like this, and then like this. So, okay. So, suppose average concentration, so it is 95% of the average concentration. Suppose this is your average concentration here, C average. So, it will go up slowly like this, sorry. So, when you attain 95%, there is the 95% of the average concentration. So if you attain the 95% of the average concentration, that is called the mixing time. So this is the way the mixing time. So that is the how much time the fluid take to attain certain average composition, right? To attain the average concentration. That is 95%, because 100% if you want to achieve, it will take a lot of time, because it is theoretically takes time. So 95% concentration, if you average concentration, 95% of the average concentration when you attain it, that is called the mixing time. So if you see the mixing time, if you compare, that is the way in the laboratory you can calculate the mixing time. And in case of the LD also, if you want to do it, some kind of tracer you have to put, and then you have to insert some amount of the probe, some kind of probe. For example, oxygen also you can take an oxygen probe, you can see when it takes to attain 95% of average concentration, if you know what is the amount of the oxygen is input into the bath. So that way also you can measure it. So and then, so you can see the mixing time variation, mixing time versus your flow rate. You can see the with the flow rate, obviously the mixing time, because the flow rate means there is the bottom gas purging. Bottom gas purging is different for different cases. For example, OBM process, obviously the bottom gas flow is the maximum, and then in that case you can find the mixing time is minimum. In case of the LD, the maximum mixing time is maximum. You can find it is a 120 second, 100, more than 100 second, where in case of the OBM process, the mixing time is only of the order of 10 seconds. So mixing time is quite less. LB process is here, that is with the 1 to 5 that is if you in the LB process, you know, inert gas purging, that is the within 1 to 5% of the gas is purged from the bottom. Okay. So mild purging LB also, and then also you can see from LD compared to the LD, mixing time basically decreases in case the LBA process also, LB process also. So some amount of gas purging from the bottom always help in increasing the mixing time. That is the mixing time, that is the how much time it takes for the pieces to be mixed up into the reactor. Okay. So hybrid process performance, if you see, then the performance you can see, that is the percentage of oxygen and percentage of carbon in the bath. Okay. What you see, for a particular amount of the carbon in a bath, okay, you can find oxygen is, dissolved oxygen is maximum in the LD process and it is minimum in the OBM process. That means for a particular amount of the carbon, this oxygen amount is very close to the equilibrium oxygen amount. And here you can find for this particular element, that is the oxygen percent in the bath is very high. It means that is the mixing, oxygen is not mixed up properly. That is the bath oxygen, when it will become very high for a particular amount of carbon. So say 70 weight percent of carbon, because solubility product of the carbon, if you see, that is the your WC into WO, this is a constant at a particular temperature. This is constant at a particular temperature. So when it is low, that means it is very close to the equilibrium value, and when it is high, that is it is much away from the equilibrium value. That is this actually this could have been the equilibrium value, and here it is you are very high. So at any point you can see the LD, dissolved oxygen, is much higher compared to any process. OBM process is this, and in this case is this. So you have a much higher oxygen into the LD process. What does it mean? If the dissolved oxygen is higher, you cannot lower the dissolved oxygen in the LD process. But in case of the OBM process, dissolved oxygen is much less. Higher is the dissolved oxygen. The turned down sample, if you have a very high oxygen and because of non-attainment of the equilibrium, then you have to use much more deoxidizer. Not only that, the implication is that if you have more dissolved oxygen, more iron oxide will be there into the slag. As a result, there is a percentage of Fe in the slag will be high. As a result, the iron loss will also be very high. Okay. So that is more important thing, is that for a particular amount of carbon, so you can find that is a dissolved oxygen in OBM process is much less compared to that of LD process. And higher dissolved oxygen means the higher the Fe in the slag, because they will be try to be in equilibrium, because higher the dissolved oxygen, higher iron will be oxidized to Fu. And so you will have lot of Fu in the slag, and then iron loss will be high. That is the problem. Okay. So, next figure you can see that only, that is the Fe loss in the slag versus percentage of carbon. For a particular amount of the carbon, you can find that for a particular amount of carbon you can find LD, your iron loss is much higher compared to the OBM process. So, OBM process is very close to the equilibrium, very close to the equilibrium, and that is why your iron loss is very less. Dissolved oxygen in the bath is also very less, whereas LD comparatively much higher. There is the dissolved oxygen comparatively higher, and then so iron loss is also higher. If compared to LDB process you can find that is the iron loss is much less, a little less than the LD. So, LD process, that is the LB process is closer to equilibrium, and OBM obviously, and LDOB where the dissolved process the iron loss is less. So, that is the comparison of different hybrid process. So, how do they perform? The iron loss in the slag will be maximum in case of the LD process. Now, so this is about the hybrid process. The main aim of the hybrid process basically in the LD process, if you want to mix up the lower part of the furnace, then you can improve the partition coefficient, or also you can improve partitioning of the impurity, you can improve, and also you can decrease the irregularities like slopping into the furnace. So, because the lower part of the LD furnace is weakly stirred. So, if you give an inert gas purging or some kind of purging, that is inert gas purging, that helps in moving the process more closer to the equilibrium. That is, you can increase the partition coefficient, partitioning of the impurities, as well as you can decrease the irregularities. Okay. So, that is the thing. Now, I will talk about this little bit of refractory practice into the LD, because this is very short, that is why I want to club it here, short presentation. So, basically in LD you have a basic refractory lining are there, and interesting some fact I have given, approximate thickness of the refractory lining is around 1 meter, and weight of the lining is around 3 times the nominal capacity of the vessel. That is very interesting. So, if it is an 150 ton ladle, then its weight of the refractory lining will be around 450 tons, that is the 3 times. And the life is around 100 hits when the wheel lining, that is the life is around, refractory lining is 100 hits, you can do the 1000 hits you can do. And with a wheel lining, there is the Dolu wheel lining, you can use a Dolu wheel lining, then the lining life become quite high. And what basically does Dolu wheel lining, that means you have a dolomite. So, when the liquid metal react with it, so the liquid is the liquid hot metal, and this is your refractory. So, when the hot metal comes to the refractory, and if you have tar impregnated magnesite or dolomite, there is a tar impregnated magnesite or the dolomite, you have Dolu and dolomite. So, what happens is that when the refractory comes in contact with the when the hot metal comes in contact with the refractory, then the carbon, that is the tar, that get decarburized. So, basically what happens, the refractory get decarburized, because it is tar impregnated, those carbon get oxidized. So, it get decarburized. As a result, you can form a decarburized layer. So, you can form a decarburized layer. When it is decarburized, then a lot of pores are forming, okay. Because of pores, then the hot metal cannot further wet this layer, okay. So, because of formation of the pores, because pores are so micropores, that is the hot metal cannot wet those. As a result, hot metal get detached with this dense, that is this refractory lining, okay. So, this basically, this decarburized layer basically separate the tar bonded portion by a thin decarburized layer. This tar bonded portion is this, and this is the hot metal, and this decarburized layer, and the hot metal cannot penetrate this decarburized layer very efficiently. As a result, this basically tar bonded portion, this portion gets separated from the hot metal. So, hot metal cannot erode that portion. there is the tar bonded refractory so quickly. Okay. So as a result, your life can be around 1000 hits, 1000 hits. And then another technique is there by which the refractory lining can be improved, and that is called slag wash or slag flashing. So whatever the left out slag is there in the LD furnace, you can adjust its composition such that you can have 13% FU and greater than 8% MgU in the slag, because FU gives the fluidity of the slag because it requires fluids too. And then what happens, and the MgU basically gives the protection. And then if you make this composition and then you blow some nitrogen through a lens, and when you blow the nitrogen, then what happens, the slag is splashed over the wall and then it adheres to the wall. So FU basically gives the fluidity to the slag such that it becomes fluid enough to wet the refractory surface, and the 8% MgU basically gives the proper protection during the steel making process. So then you can give a slag wash. There is a slag flashing. Basically you are giving a slag wash on the refractory wall, and if you do that, then the lining life goes beyond 2000 hits. Okay, life becomes 2000 hits. So this is very small about this refractory lining. Okay, and these are the reference. So what I said in this lecture is that a spectrum of hybrid process have evolved to take care of deficiencies of conventional LD furnace. Deficiencies means there is a lower part is not stirred. Now with the hybrid blowing, you can increase the stirring. You can decrease this deficiency of conventional LD, or to treat hot metal of special composition, because if you want to treat a very high phosphorus hot metal, then LDAC or LDHC, those type of process where basically you inject the lime either from the top oxygen lens or from the bottom lens. Okay. So then combined top and bottom purging, called the hybrid blowing, have given rise to several process variants we know. And then oxygen purging from the top, inert gas purging from the bottom is very common, called the LB process, to enhance the mixing of the lower part of the ladle to achieve near equilibrium partitioning and to avoid the slopping. Lime powder injection with oxygen lancing is used to treat high phosphorus hot metal, and 100% bottom oxygen blowing OVM provides a maximum partitioning of impurities, but it suffers from the nozzle maintenance, as I said, because when you are 100% oxygen from the bottom, the nozzle tip will be heated up very good, because all the oxidizing reaction will take place at the tip. As soon as the oxygen coming out, it reacts with the impurity, forming a lot of heat. That's why its nozzle maintenance is a problem. Although it uses some hydrocarbon protection through the annular portion, such that when the hydrocarbon come, they do the very endothermic reaction. As a result, it try to compensate the heat generation at the top of the nozzle, but still nozzle problem is there in the OVM process. Otherwise, OVM process was fantastic because it attains the equilibrium and your impurity partitioning can be attained to the maximum extent, but problem is nozzle maintenance. So from considering all this thing, there is the LD process modified with the bottom inert gas purging, right? That is called the hybrid blowing process, appears to be the best solution today. That's why this process is running very well. That is the LD process along with bottom inert gas purging, LB process. Those processes are mostly popular and going on, and because this basically solves the major problem of the LD vessel, that is the lower part of the furnace that is weakly stirred in case of conventional LD process. So if you give some bottom inert gas purging, you can overcome these deficiencies of the conventional LD process. Okay. So and this conventional, that is the hybrid blowing, today is running very nicely and it is producing results, and hybrid process is now very popular. That is the LB process. Okay. But OVM was the most promising, because in case of the OVM you can be very close to the equilibrium, but the problem is the nozzle maintenance. Thank you very much.